Okay, so we'll start from where we left off yesterday. Yeah, and after hearing some of that amazing kind of mathematics that Chandan talked about, we'll get back to our simpler world of linear algebra here. Okay, so yes, another thing is that the tutorial today, I thought we'll keep it a bit like yesterday. Yesterday we kept it, you know, I had proposed some things we could look at, but actually we kept it a bit free and we had a lot of discussions on various points that you found confusing. So let's keep it that way in today's tutorial too, okay? So I can go through again some things that we did in the lecture or other doubts that you may have, conceptual doubts, etc.
Yeah, that's
You said something?
Yeah, that's fine.
Yeah. Okay. Fine. So yesterday where we stopped was that we said that okay. So let's just say remind ourselves, where are we going, right? So we have some set of systems which can be modeled as chemical reaction networks, and we are saying that there is this property which is called deficiency, which can be written, which can be written like this or like this. And we saw yesterday that these two are equivalent with some, with thinking about, you know, images and kernels of matrices, etc. We kind of understood that these two definitions were equivalent. So if this deficiency was 0, what we said is that there is an easy way to solve that chemical reaction network by just looking at this matrix, the A matrix, okay, which I've written for our favorite example. So this A matrix, you know, so just looking at the 0 eigenvector of that A matrix, we said that we are able to find the solution, which will solve the rate equations. The rate equations being given by that. Okay, X column vector, Y matrix times A matrix times some psi equal to 0. And we said that if deficiency is 0, this psi is just basically obtainable by looking at this A matrix. Okay, so we will talk a little bit more about that. So we'll also do an explicit example. So we try to get a 0 eigenvector of this A matrix and then just see that if deficiency is 0, we are always able to write it in terms of these concentrations, you know, which could be nonlinear combinations of these species. But if deficiency is not 0, we'll not be able to do that. So we will see that, and that basically will get us to the end of this deficiency 0 theorem. As we saw when we took a look at the statement of the theorem, and that was only a partial statement of the theorem. I mean, there's a lot more to it. Like there is stability of these solutions, local stability. So I think what's proved is what's called asymptotic stability. For if you begin from somewhere close to a fixed point, you reach a fixed point. There's also this open problem called global stability, which I think all these mathematicians are very interested in. That I think there is only a conjecture so far, a global stability conjecture, even for these deficiency 0 systems. Okay. So there's a lot of aspects to the deficiency 0 theorem that we won't go into. But instead, what we will do is we will go into some stochastic modeling, presumably tomorrow. So today we stick to our deterministic systems. Okay. So as I said, kernel of A, remember, kernel was what we call the null space, the 0 eigenvector. Kernel of A is enough. How do we know that A has a kernel at all, in the sense that how do we know that it's a non-zero set? So the vectors which lie in the kernel of A, how do we know that it's a non-zero set? So for example, you know, if you take a, you know, the identity matrix, the only thing that it can set equal to 0 is a set of column vectors. I mean, a set of zeros. Similarly, if it's an upper triangular matrix, you know, we'll take an example of that, or lower triangular for that matter, I suppose. So there are some matrices which, you know, don't set anything to 0, or rather the only thing that they can set equal to 0 is 0 itself. So how do we know that this A has a kernel? How do we know it's how many, you know, independent vectors lie in that kernel? How do we know that that kernel has positive elements? Remember, we are talking of concentrations or fractions. We definitely do not want anything negative there. Okay, so how do we know that the eigenvector, the zero eigenvector, is actually a physical quantity, right? So all those things we learn from this Perron-Frobenius theorem. So let me show it to you here. I'll share screen. Here. Good, it showed up on the screen. Okay, so this was our deficiency zero theorem, and so basically you see that there's a lot of stuff there related to stability and so on. But we will just, so we will today, by the end of today, we would have understood this much. Weakly reversible, has deficiency zero, rate constants are positive, and mass action kinetics. And then that means that for any choice of rate constants, there's precisely one fixed point in each stoichiometric compatibility class, and this solution is complex balance. So this idea of complex balance also we'll talk about, and it's going to be important when we do some stochastics tomorrow. Okay, so that was the thing. Now let's go to the Perron-Frobenius theory. So I've taken the statements. This is also something actually quite elaborate. So I'm just showing you some kind of modification or at least a restatement of that I've taken from the John Baez and Biamonte book. I didn't know this, but first apparently there was a theorem by Perron related to just an n by n real matrix. And if it's positive, if all its entries are positive, then so a positive matrix is defined. So this is just a definition of a positive matrix. If I say it's non-negative, it means that some of its entries could be zero. Okay, so first was a theorem by Perron who showed that, and this was I think early 1900s or something like that, showed that if it's a positive square matrix, then there is a positive real number R, such that R is an eigenvalue of this matrix. And any other eigenvalue strictly less than R, okay, absolute value of this eigenvalue is strictly less than R. And there is a positive vector. So that's the important part. So because the kernel of A, we'll be able to understand in other ways. You remember our rank nullity theorem, etc. But what about the positive eigenvector? That's important for us. This theorem of Perron guarantees it, at least if it's a completely positive matrix, okay? What if it's not just a completely positive matrix, but rather non-negative? So if some of its elements could be zero. So that's why this theorem was taken a bit ahead, I think a few years later, also in the early 1900s by Frobenius. And so that's why it's now called Perron-Frobenius. And that Perron-Frobenius theorem now says, had to make the further constraint that it's also irreducible. So Frobenius generalized it from positive to non-negative, but then had to make it irreducible. Okay, irreducible, in our language is one linkage class, so one connected component in our graph. So if it's irreducible and it's non-negative, then again there is this positive real number. It's called Perron-Frobenius eigenvalue. And it's an eigenvalue of t. There is a slightly weaker condition here. You see the absolute value of this lambda less than equal to R. So remember, Perron showed that it's strictly less than R, but then that was a different matrix, a positive matrix. In this case, this is a non-negative matrix. It's less than equal to R. So basically, if something has eigenvalue 1, the absolute, I could also have an eigenvalue -1, okay, which of course then the absolute value is the same. So there can be some degeneracy that way, but there is still a positive eigenvector. Okay, so then you can ask the positive eigenvector related to this eigenvalue. Okay, so then you can ask how does it connect with our A matrix? Because not only is it non-negative, there are also some, like negative elements along the diagonal, right? So what about that? So for that construction, I think one can you can do in this particular way, that you take your A matrix and add an identity matrix to it. The identity matrix being multiplied by some constant, which is large enough that it makes all diagonal elements also positive. Okay, so then you got a non-negative matrix and irreducible, let's say, for the moment. In that case, then one can show that the Perron-Frobenius eigenvalue for this T matrix is then exactly this number that you multiplied your identity matrix with, or namely the fact that your or the A matrix actually has an eigenvalue 0. So one can show that. As I said, it's related a little bit to the various constraints you can impose on this maximum eigenvalue as everything there. Okay, so those of you who are interested should definitely look this very important theorem in linear algebra up. And as I said, there are many aspects to it. This is just the aspect that we need that I'm mentioning here. So as long as A is reducible, it has a unique positive eigenvector associated with the 0 eigenvalue. Okay, so we are safe. Of course, then you could say that the A that we are looking at is not reducible, or rather irreducible. Okay, so let me get rid of this now. So that doesn't matter very much for us. We will just, for each, we are satisfied with the fact that this theorem applies to each one of these components. Okay. So that's enough for us, that it applies to each one of these components. Okay, so as I said, the positive eigenvalue part is actually the sort of part that you and that's not quite obvious. From the rank nullity theorem, which we talked about yesterday, it's you can guess that there has to be the kernel of this. So the kernel of this, for example, if I take this block, you can guess that there has to be only one eigenvector in the kernel of that. Okay. The fact that that is the other eigenvalues are sort of have an absolute value less, that the eigenvector is completely positive, all that is extra and more, more complicated stuff that the Perron-Frobenius deals with. But the fact that there is one eigenvector with 0 eigenvalue, you can guess, because if you look at this matrix, and I think we discussed this a little bit in yesterday's tutorial, if you just look at this block here, okay, then you see that there are, the rank nullity theorem says rank plus nullity equal to 3 in this particular case. This block has number of columns 3, 1, 2, 3, right? So, and the rank of this matrix is 2 because there are 2 independent column vectors. If you see, there's this one and this one, or this one or this one. The other column vector can be thought of as some linear combination of these other 2. So basically, with this kind of structure, you're guaranteed that you have one eigenvalue. I mean, you do definitely have a kernel, one eigenvector in the kernel of this matrix. Okay, another way to see it also is that these matrices, so taking the transpose of a matrix doesn't change its spectrum. So if you we know that 1, 1, 1, okay, and we are going to use that, is a left eigenvector with 0 eigenvalue, right? Because the column is adding up to 0. So then we are guaranteed that there will be some right eigenvector with a 0 eigenvalue. Okay. So just the fact that there is a 0 eigenvalue is something we could guess in different ways. But as I said, this Perron-Frobenius has many other aspects, such as what's the nature of the eigenvector which corresponds to that 0 eigenvalue. It has the physical properties that we want. The fact that the other eigenvalues are less, the absolute value is less than this 0 eigenvalue, which guarantees actually for solutions of this matrix global stability. Okay. Because I mean, if all the other eigenvalues basically ensure that wherever you begin, you decay to that solution, right? So So as I said, please look up Perron-Frobenius, okay, if interested. It's something that we use a lot. Okay, so that was this theorem. So we are guaranteed that, so if deficiency is 0, then instead of solving our rate equations, we could just look for an eigenvector. Okay, I put psi hat here now because there is still a step left, right? Which I'll mention a bit. Which I'll mention. Yes.
So, so kernel of A is two-dimensional. Is that right?
In this particular, yes. In this case, with 2 blocks, yes.
Two-dimensional. So image okay. So then, and what is kernel of Y? No. So how do you see that image of A intersection kernel of Y is zero? Is that zero? Is zero-dimensional? That's what you're saying, right?
Yes. So that means that there is no vector. So there's in that if I'm thinking of the set of vectors which would satisfy that property, that set is 0, in the sense that that set has
yeah, no, but
cardinality 0 or whatever you may find. Yeah. Yes.
Yeah, but I mean, this you showed yesterday, or it's clear. I mean, the fact that this intersection.
So that is almost okay. So okay, let's see how. So you're saying why is that 0?
Yeah, I mean, why is that image of A and kernel of Y have no common eigenvector? Like, don't have a, I mean, are in different.
They could, but so okay. So they could, but if deficiency is 0, then they don't. You see what I mean?
Oh, okay. You're saying because deficiency 0, we have independently shown.
Yeah, so we have, okay, so this is also, you could think of as a definition almost of deficiency.
Right, yeah. So I should be able to see it from the structure of these matrices, right?
Yes. You should be able to see it from the structure. So let me proceed a bit and maybe we can get to that point. Yes, you're right. So, okay, so this you could think of as a definition. We also had another definition. So yesterday we showed that these 2 definitions were sort of similar.
Right, okay.
But I mean the same, not similar, they were the same.
So from the other definition, it's easy to see that it's 0, right? From the C minus L minus S.
It's a definition that you can easily apply on any network and quickly check something is 0. Yes.
Right. Okay.
See, this one is a bit harder. I mean, if I have to use this definition of deficiency for that network, to understand what is the deficiency of that network, then I have to do a bit more work. I have to set up all this business and take a look at them. But this definition is very easy just by like inspection, almost visual inspection of.
Yeah. Okay. Yeah. So that's what I'm saying. From that definition, it's clear that it's 0.
Yeah.
Right. Okay.
You mean it's clear that this is 0? It's clear that what is 0? Clear that the definition, I mean, deficiency of that is 0, or are you saying is it clear that this is 0?
No, I'm saying if I use the fact that delta equal to C minus L minus S, then for this set of reactions, it's clear that this delta is 0.
Yeah.
That is easier to see, but from this, it's more complicated to see, I guess.
Exactly, but this is what we need now to get further.
Oh, okay.
Because you're right. So this is why this is such an important definition too, because that's the thing that you can just automate almost write a code and then put any, like this example that I showed, people were looking at metabolite networks with, thousands of reactions. You can put it through, some code that you write, which just checks for these numbers and it'll spit out some deficiency for you. So that is a very easy thing. And for a network like this, you can almost just look and say that it is 0.
Okay.
But this definition is also very important because that's like how we are going to proceed a bit further.
Right,
That's sort of showing you like the structure behind, like the mathematical structure that lies behind those rate equations that leads to all these results in the first place.
Yeah. Okay. Yeah.
So,
Thanks.
yeah, but yeah, so let's say, you know, if something is unanswered, let's come back to that. So if so basically, you know, so we showed yesterday that, you know, this thing and that thing are the same, and the way that we did that was to say that I won't go through the steps, but let me just mention that the way that we did that was to say that if you can see this part of the board, right? Yeah. So if I'm looking for a solution like this, right? So if I'm looking for y of a, uh, if I'm looking for y of a psi is equal to 0, because it's a, you know, a matrix equation of this sort, only two things could happen. I mean, either a psi is 0 or a psi not equal to 0. You agree? Those are the only two things can happen. If a psi is 0, problem solved. Okay. If a psi not equal to 0, we still need something in order to satisfy this, and that is y of a psi. And these are the two conditions. Implies deficiency 0, implies deficiency not equal to 0. Okay, so that this is what is here. If this was not 0, then there would be this would be non-zero delta. That means that there are some vectors that live in the kernel of in the image of A and the kernel of Y, right? Because A and Y are coming in this particular order, acting on our psi. First, the A acts on the psi, then the Y acts on the psi. So that's important. That's why we need the image of A and the kernel of Y. Okay, so that's where the definition came from. And then we showed that by breaking up the image of A into the image of YA and the image of A but the kernel of Y. Okay, so breaking it up into these two different exhaustive possibilities, we could add everything up, and then we got this relation too. So those two relations are similar. Okay, so let's take an example of a network where the deficiency, you know, is not 0, just so that you get. And I think one of you asked something like that in the tutorial yesterday. So basically, okay, so how far have we come? Okay, so we understood a little bit of this mathematical structure here. We are saying, okay, fine, like at least for deficiency 0 networks, that's what the theorem is holding for. We are it's enough if we take a look at this A and look at the 0 eigenvector, okay, for this P. Or 0 eigenvectors, as it were, but some linear combination of those 0 eigenvectors. It's enough if we look at that for this A. And we are guaranteed that such a thing exists for this A because of the Perron-Frobenius theorem. Okay, so we've used a lot of these results. Okay, but there's one last step left, okay, and that's the last step that we will deal with today. And that is that if A psi is 0, okay, so let's see that I find this. So let me say that by some, you know, because it was after all just a simple example with matrices and stuff, I didn't solve any rate equation, I didn't do anything. I took the A matrix relevant for my network and I got a 0 eigenvalue. Okay, let me call it psi hat. How do I know that psi hat is this psi? Remember what that psi was. That psi was not some totally trivial thing. It was actually some y, a, and b. I said that we could write it as x to the y. You remember it was this this vector for that matrix. Let's write the psi here. I don't know. Yeah, I think you can see this. 1 xe xs xe xs xes x. XE, XP. Okay, psi has to, oops, the XP got left out of your screen, I think, the XE, XP. But nevertheless, you've seen this plenty of times before, right? Oh, I guess, is a lot of it getting let out from the screen? Maybe I'll write it a little bit.
I think it's okay.
Okay, fine. Okay, so we will write it many times, right? But you've seen this side before. So it's this set of concentrations, XE. I'm writing it in the same order. So the first element is 1, XE, XS. Then remember, then I got an XE times XS. Okay, so there is a constraint there. If I find an XE and I find an XS, then that next element had better be a product of those two if I want to be consistent. It can't just be anything. You see what I mean? And that thing there, that the psi corresponding to that element there should be an XE times an XP. So I don't have that much, I mean, play. I have some play. I don't have that much. So am I able to satisfy and get like a meaningful solution to my rate equations just by finding the psi hat? Am I able to, in other words, put it in this form x to the y? You remember how we said this x is a column vector, y is this matrix y, and we can sort of think of it, how we can think of taking the power and getting these sort of these elements, our psi elements out of it, okay? If you don't remember, don't worry, we'll take a look at it. But basically the idea is, are we able to do that, okay? Finding a null eigenvector of A is not a hard problem. Am I able to actually satisfy my rate equation with that? Getting all the concentrations correctly, satisfying all the constraints that this complex is just a product of these two species, etc., etc. Okay. And just to show you that, that's not necessarily always the case, let's take a simple example. Let me get rid of this. I'll write it on another part of the board later. Let's take a simple example of some, something like this. P goes to 2P goes to 3P. Some kind of birth-death process you can think of, okay? Which of course is sort of solvable. You can go indefinitely, 4P, 5P, okay? We mentioned this in the tutorial yesterday. And this has deficiency 1. Why? Because you take our definition. Delta is equal to the number of complexes, 1, 2, 3, 3 complexes. Number of linkage classes, only one connected component. And the stoichiometric subspace, there's only one species. Okay, so just one. The number of species doesn't necessarily give the stoichiometric subspace, of course. Okay, as we have seen, there can be constants, etc., that reduce the dimension that the sort of rate equations live on. It's very easy to see that the reaction vector here is just +1, and the reaction vector, the column vector which tells me what this reaction is just +1 or whatever. So there's just one vector here, which is this one number. So basically the deficiency is 1 for this network. So the deficiency 0 theorem doesn't apply. Okay, let's just see, but nothing is stopping me from writing an A matrix and finding a 0 eigenvalue. Okay, there is an A matrix. Of course, every such network has an A matrix. So let's write this one down. Then I need to know all this stuff here. Okay, let's do it this way. K1, K1 bar, K2 bar, K2. Okay, so the A matrix, remember, I just choose some sort of labeling for my rows and columns. And then I can just write it by just inspection. P disappears at some rate K1 and goes into 2P. 2P disappears at some rate K1 plus K2 bar, but with the K1 bar it goes into P, and with the K2 bar it goes into 2P. And 3P, let's see, there's a K2 here, and K2 going into 2P. Okay, so columns are adding up to 0 as we want, etc. And then I can find I can find a 0 eigenvector. Nothing's stopping me from that. A, B, C is equal to 0, 0, 0. right? So let's find the zero eigenvector. If you find it, which is not a hard problem at all, okay, very simple. So let me just write this down. So the zero eigenvector then, I'll use this part of the board. Then I have to be sure I'm not blocking it here. If I haven't made any mistakes, okay, so please check. It's just this. Okay, actually what it is not important for the point that I'm going to. But you can see that I have a little bit of play here. Because after all, if I find a zero eigenvector, this is going to be very important for us, okay, when we talk of how much leeway we have with finding zero eigenvectors. So that if I have a zero eigenvector, I can multiply by a constant, it's still a zero eigenvector, right? So I have some, A that I can fix in some way. Okay, now let's see if I can fix it somehow by demanding that this should be the same as, let me put a question mark. Can it be the same as our psi vector? The psi vector here is just how the complexes are denoted in terms of the species, right? So it's just x of p square, x of p cube. Can I ever choose an A such that that works? Okay. So I can say, oh, okay, x of p square is like that. So why not put A equal to k1 by k1 bar? So A will be k1 by k1 bar. This will be k1 by k1 bar square. But then what happens here? Okay. So unless k2 bar by k2 is equal to k1 by k1 bar, I can't get a consistent solution, sort of transforming my zero eigenvector of A into the form that I need to be for it to make sense as concentrations. That making sense? So this is the nice part of it. And if deficiency is not zero, we'll never be able to do that. Never. I mean, I can always find a zero eigenvector of A. As I said, A will always have a zero eigenvector. A is always of this nice form, stochastic matrix. But I will not be able to transform it into, into this form which it should take in order that those numbers, those A, B's, and C's make sense in terms of the concentrations of my chemical reaction network. On the other hand, if deficiency is zero, I'll be able to do that. Okay, so that's so let's just try to understand. So this is the last part of the theorem. Let's try to understand why are we able to do that if deficiency is zero? And everything starts from this condition here. Okay, so let's do that. So we'll have to, I'm afraid, do some more linear algebra. Okay, some more kernels and images and all that. So let's do that. Yes. Please feel free to interrupt and ask absolutely anything, because that's a good way for me to know also if I'm being clear. Okay. Okay, so now we are going to do this, and this is maybe the trickiest, maybe the most, the trickiest part of the whole thing, because a lot of it, was we sort of went on a ride along with Perron-Frobenius. So we thought, okay, a lot of the work is done, but now we actually have to do some work ourselves. So deficiency zero implies dimension image of A, kernel of Y is equal to 0. Okay, what does it mean dimension of something is 0? Now it's time to not just talk of dimensions, but actually talk about what vectors live in those subspaces, okay? So that just means that image of A, I think one of you had a question about that. in the tutorial about this sets of things that exist here. Okay. That just means that this, if I'm thinking of what's the set that lives in this image of A and kernel of Y, it's really the null set. Nothing's there. Okay. But now let's do something and look at the, there's a word for it. What's it? The orthogonal subspace of this space. Okay, so these are spaces. Let's look at the orthogonal subspace of this space. Okay, here what is going on, we don't know. But here we know that it's going to be just the entire space. My sort of space that I had, you know, was the space of these complexes. You know, so these things were acting on vectors, which the dimension of which was given by the space of these complexes, right? The dimension of that space is just the number of complexes. In this particular case, six columns, 1, 2, 3, 4, 5, 6. Okay, so in the orthogonal subspace to that is the entire space in some sense. If you know, if this was just a 0, then the entire subspace, I mean, the entire space rather, it's not a subspace anymore, is orthogonal to that. Okay. Now, but now we have to understand a bit more what's going on here. Okay. And now you'll have to, it's one of those things that it's a bit hard, you know, so you just have to stare at it a while to get used to this kind of thing. Namely, image of A orthogonal is equal to the kernel of A transpose. And the kernel of A orthogonal, okay, any matrix, A for the moment can be any matrix. Image of A transpose. So we are going to use these two, okay? So let me just try to motivate this. Or is it like crystal clear? No? So let me try to motivate this a bit. As I said, there's a lot of linear algebra that I had forgotten. So there's, I suppose, different levels of understanding these things, but for us, it's good enough if we just get a feeling of why that is true, right? So let's take the case where, let's take the case, for example, where kernel of A is 0. Like I said, remember that we, so example. So imagine a matrix like that, which is just, you know, I mean, there can be any things there. So you immediately see that the kernel of this matrix has to be 0 because the, okay, I'm blocking it a bit here. You can see that the kernel has to be 0 because each of these, the dimension is three columns, but each of these column vectors are independent of the other. So the rank is also 3. So from the rank nullity theorem, there is nothing in the kernel, basically. So it can, of course, set something to 0 if everything was 0, but we're not counting that. Okay, so that what this is saying is then the A transpose is okay, let's look at, yeah, so this one. So what this is saying is that if the perpendicular space, of course, to a 0 is the entire space. So which is the image of A transpose, which is, okay, so how should I say it? A kernel, okay, so let's take a step back. So what exactly does a kernel mean, right? So suppose I have something, let's call it A, B, C, D, X, Y is equal to 0. So how do I get the kernel in some sense? The kernel I get by multiplying this xy by the row vectors a, b, and cd. So ab is one row vector, cd is another row vector. And when I multiply this xy by that, I get a 0. So you can think of the xy as being perpendicular to AB. You see what I mean? So it's perpendicular to the row vectors. So and then if I transpose this, these row vectors become the column vectors. If I take the transpose of this A, B, C, D transpose, this becomes, of course, A, B, C, D. So any statement about the kernel transforms to a statement about the image, because now we are looking at this A, B, and this C, D. So if there were two, if you know, there were the kernel of this thing was 1, then that transforms to the image of this transposed matrix. I don't know, does that make sense? We can discuss this, of course, also more in the tutorial. So basically, you know, the kernel is sort of talking about what sort of vector is perpendicular to the rows of a matrix. And then when I transpose that matrix, those rows becomes columns in the transposed matrix. So now, you know, that's how the kernel of something is related to the image of the transpose. Okay. I hope that makes a bit of sense. Let's take another example, maybe. So basically here, all that I was saying is that the kernel of A, if it was 0, the orthogonal subspace will be the entire, you know, we'll have 3 vectors, basically, the image of A transpose, which are basically these 3 vectors, this, and this. In this particular case, it doesn't matter. I can also take the columns, but basically it's the image of the A transpose will basically be these row vectors. All 3 of them exist in the, play a role in the image. Any questions? Let's take another example. Maybe you see this also. Maybe the example was the same one we took in the tutorial yesterday. So these are these 2 things. Let me do it here. So suppose I have a matrix like this, 0, 1, or maybe let's, okay, 1, 0, 1, 1, 1, 0, 2, 1, 1. So the number of independent column vectors, which is what the dimension of the image is. Okay, so I think I should be a bit careful how we are saying this, right? I mean, the image is okay, just something which a matrix acts on and spits out, let's say, which is non-zero. Okay. But then you can also ask of the dimension of this image space. And the dimension of this image space in this particular case is 2. Why? Because this is an independent column vector to this one, but this one is just a sum of these 2. So the dimension of the image space is 2, and the 2 vectors that live on that in that image space are sort of like that. Okay, and then we can say that the image of that matrix is then any linear combination, can be written as any linear combination of those 2 independent vectors, right? So what is the orthogonal subspace of this image? So the orthogonal subspace of this image would be the vector perpendicular to those, right? It will be the orthogonal subspace would be the vector that's perpendicular to those 2 column vectors, which is the same thing as the kernel of A transpose, because now that A transpose converts those column vectors into row vectors. Okay. Because the kernel is something which is perpendicular to the row vectors. If I wanted the orthogonal, subspace of the column vectors of some matrix, it's equivalent to transposing it and looking at the kernel. Okay, so these are just little things one does to see the connections between them. Again, we can discuss this a bit more. But if we just accept that this is how it is here, and these are the connections between our rows and columns and transposes and images and kernels. Okay, I should say actually one thing. Since everything is real, I'm just doing a transpose operation. I think if things are complex, it's in the Bayes and Biamonte book, they do a dagger operation. So I think it's more general than just a transpose, right? So for our case, we are talking of concentrations. Things are not complex quantities, etc. So this is good enough for us. Okay, so if we accept this stuff here, okay, these two relations, then what we have, okay, so what we have then is image of Y transpose plus kernel of A transpose is equal to RC.
Supriya, we can't hear anything. Supriya, we can't hear anything. Oh, she can't hear us.
You need to write chat actually. It also happens.
That suddenly muted me actually. So how long was it muted? I hope it was not muted too long.
Maybe a minute. Just when you started discussing this relation, image Y transpose plus.
Yeah, okay. I don't know. It happened quite suddenly. And then I heard a sound saying recording in progress. So something happened there. Okay. Okay. So we got this far, right? So even if it's a little bit mind-boggling to keep doing transposes and doing images and kernels and all that. The information that this thing has is not hard, right? All that it's saying is that if I took all the vectors which lie in this set, and I took all the vectors that lie in this set, I should be able to describe any vector in that space. That's it. Okay, that's all that that's the information that it's carrying. Okay, one set is the image of Y transpose, the other set is kernel of A transpose. That's also going to be important for us. But basically, the sum total of the vectors in that set span this space. So let's take an example to see that, right? With our enzyme kinetics example. So let's understand that in the case of the example. Okay, examples are a little bit lowbrow way of trying to understand things, but I always find it very useful to do a lot of those before it starts to make sense. Okay, so I'll keep this here. So remember, image of Y transpose, or maybe I'll write it somewhere that I don't have to erase it off. That's just a way of saying that any vector in the 6-dimensional space, if this is my example, is going to be describable by those. And that's only happening when deficiency is 0. Okay, because if deficiency, I wouldn't have got this. This I got as the orthogonal subspace of 0. If my orthogonal, I mean, if my deficiency was not 0, there was, let's say, one vector living there, deficiency was 1, then the orthogonal subspace of that would not be the full space, right? They're not guaranteed that any vector in that space is going to be describable by these two things. Okay, and that's the sort of crucial condition. Okay, so let's just work this. Let's just see that very fast for our little example here. So what was Y transpose? I should do the transpose of this thing, right? So image of Y transpose means that I'm talking of the image of this matrix. 0, 1, 0, 1, 0, 1. 0, 0, 1, 1, 0, 0, 0, 0, 0, 1, 0, and then okay. Remember how we got our Y matrix? It was just our stoichiometry. Rows are labeled by the species, columns are labeled by the complexes, and I just keep track. I just run through a row and say, oh, E, it's here once, it's here once, it's here once. S, it's here once, it's here once. ES, only there. P, only there. Okay, as simple as that. Okay, now when you look at these image of these things, remember the space, the dimension of the space was the number of independent column vectors. Okay, so we easily see that there are 4 independent column vectors here. So dimension of the space is equal to 4. Dimension of this image space is 4. So, and the kernel of A, we see that the dimension of the kernel of A is 2. Why do we see that? Because, no, A transpose, remember. So A transpose is a bit simpler than A when you're talking of the kernel. Any guesses why? Because remember, because the columns were adding up to 0, these things were adding up to 0, right? 1, 1, 1, 1 was always a sort of 0 left eigenvector. Yes?
A is also like we can see it's 0. And A transpose, like they look similar, right? A and A transpose.
They do. But there is one difference, right? In the sense that now I have a very simple 0 eigenvector. Because the 1, 1, 1, 1, 1 was a sort of left. It's guaranteed to be a left eigenvector with eigenvalue 0. And then for the transpose matrix, it becomes a right eigenvector with eigenvalue 0. Making sense?
Yeah, okay. Yeah, thank you.
So basically, we have 2 eigenvectors here. We can even write them down. 1, 1, 1, 0, 0, 0. And 0, 0, 0, 1, 1, 1. Okay, and any vector should be, I mean, any vector now in our, could you see that? Yeah. Any vector now in our 6-dimensional space should be describable as some linear combination of this and this and this one and this one and this one and this one. So that was basically what that statement means.
Okay, so Supriya, it's not clear why it, I mean, in this case, it's easy to see they're linearly independent, but in general, because this Y looked like some independent thing from YA, and somehow the image of this and kernel,
Yeah, so
it's not obvious, right?
No, it's not obvious at all. So that's why this is such a, it's such an interesting sort of non-trivial statement that y and a are looking like two different things, really. One is the stoichiometry, one is the adjacency of the graph. They come together only in this rate equation. So we just know only that d by dx y a x to the y. So it's not at all obvious that it's the case, but when you take care of the dimensions of this thing, you see that it has to be somehow. Okay, so that's not obvious at all. I don't have some very intuitive feeling, actually. If any of you do, please, let's discuss that. Okay, as I said, it's things that I try to learn on my own a bit, and not really had a lot of people to discuss this with either. So it's nice for me to have this opportunity now. So as I said, you can see that this is the case here. It's generally the case, and it's generally the case for a zero deficiency network, and this is going to be important for us. Okay. Okay, and why is it important for us? We're almost getting close to the end here. So what does this mean? It means that suppose I try to short circuit someone told me, okay, solve these rate equations. And then I saw, oh, it's deficiency 0. Then instead of solving the rate equations, I just find a 0 eigenvector for this, okay? Let me call it psi hat. Now, because of this Perron-Frobenius and so on and so forth, I know that this psi hat has positive components. So nothing is stopping me from taking the log of it. So let me just take a log of it too. Okay. So let me take a log. You'll see that the log is just in the end, we won't need to do that, but it's just for one particular reason.
So there are two psi hats, right? Two possible psi hats.
Yeah, you're right. So there are, but let us take something, so let's take one vector which is non-zero everywhere, just because I want non-zero concentrations, right? So you're right. There are two independent zero eigenvectors. Let me take some linear combination of them because I want some non-zero concentrations for everything eventually.
Okay. Yeah.
So let me take that psi hat. Okay. If there was only one block, there would be one eigenvector. If there are two blocks, there are two. And the blocks, remember, are connected with our linkage classes. Okay, so the block structure directly just follows from the graph, because this whole thing is just a adjacency matrix you can think of on the graph. And this is where the word complex balance comes in. Complex is not complex numbers. Complex is these things which we are calling complexes, right? This matrix is just telling you something about one complex going to the other, nothing about species, how species numbers are changing, just how, this complex into another complex. It's just encoding the exact information that's, you can see this, right? Yeah, this on this graph. So basically solutions, anything that lies on the kernel of this is going to be called complex balance. We'll see. Or rather, we'll discuss that. Okay. So this log of psi hat is also some, it's a vector living in the space. So therefore, I should be able to write it as some combination of the kernel of A transpose. So imagine that I take a generic vector in the kernel of A transpose and I call it alpha. And now I take a generic vector, now I take a specific vector in the image of Y transpose, okay? Because that specific vector as good as any other vector, right? So, and that specific vector is this one. So let's see. Y transpose log X. You remember our little exercise from yesterday. We showed that X to the Y, this psi, let me write this here. think you can sort of see it. 1 x e x f e. I can take a y transpose and act it on an x vector with the species and kind of get that one. You remember we did that exercise yesterday. You can just try y transpose acting on a column vector of the species. Column vector of the species is just x e x s x e s x p. Okay, I mean, I don't mean that these, so this is our psi and this is our x. Great. You can still, I think that's still visible, that part of the screen. So these are yeah, a little bit, yeah, so it's a little bit magical sort of, but in the end, it sort of follows from the fact that, from this statement, okay? So anything, so this is a vector in the image of y. And that's what I want, okay? I mean, that's what I want. I can write it in terms of a vector in the kernel of, I mean, the right eigenvector that I wanted. Okay, so that I wanted here. So the psi hat was just something that was living in the kernel of A. But in the end, I want something that looks like that, right? Because this is the right psi. I will be able to write it in terms of this if I also take into account the two vectors which, a linear combination of the two vectors which lie in the kernel of A transpose. Okay, so maybe that's like really terribly confusing. So let me just do this example. Okay, so let's go to the end of this and then we'll do a little example. So implies e to the minus alpha psi hat, okay, exponentiating both sides, is equal to x to the y. And so e to the minus alpha is like, let's see. Okay, so e to the minus alpha is a vector in that particular case. That's something that looks like this, A, B, B, B. It's a linear combination of the two vectors, okay? So all that it means is that okay, so this psi hat is what I just got out of doing nothing but finding a zero eigenvector there, ensuring that I get a eigenvector with like all positive components. I mean, I'm ensured that I do, but I take some linear combination of the two independent zero eigenvectors and I get some eigenvector, which is a zero eigenvector. Okay, I'm guaranteed that that zero eigenvector can be written as x to the y. Okay. By this trick, the fact that these vectors span the full space, therefore any vector should be written as that. So let's take a little example. Or rather, we aren't fully done actually. We are not fully done. So let's just take the two more steps to get done completely, and then we'll take an example. So why did I write this as that? Because this was the linear combination of our of the vectors that lie in the kernel of E transpose. Some A, I can call it A or E to the A, it doesn't matter. It's some constant multiplied by the one eigenvector that lies on one block and the one zero eigenvector that lies in one block and the other zero eigenvector. Right, that is a generic vector that lives in this space. Okay. Okay, so e to the alpha, when I write e to the minus alpha, in this particular example, this is what it means. Okay. So what are we doing? Actually, there is a very interesting thing we are doing here, right? So we are saying that we are finding so maybe this will make more sense, rather than these steps. We are finding a zero eigenvector or some combination of zero eigenvectors which have non-zero components, all non-zero components. And then we are using a little bit of play that we have in that if I multiply the sort of one block by, so the zero eigenvector of one block by a constant, and I multiply the zero eigenvector of the other block by another constant, no problem. Okay, it's still a zero eigenvector. I have that play. There is some symmetry hidden here. In the linkage classes, I can multiply the eigenvector by a function that's constant on one linkage class, the other eigenvector by some other constant that is constant on that linkage class. These two constants don't have to be the same, but I'm guaranteed that it's still a zero eigenvector. Is that making sense? So there is a symmetry here, and I'm just using that symmetry to ensure that now any solution I have can be written as x to the y. Okay, so this is a component-wise multiplication, right? So what I'm doing is that I'm taking, if I find the zero eigenvector of this one, okay, then I'm multiplying the, yes.
Sorry, so alpha is a vector in the kernel of A transpose, is it?
Yes.
Okay.
And e to the minus alpha would just be, I mean, it's like I do logs and e's and all. I just do component wise. Yeah. So I just do it in that way. So, okay, so whether I call, yeah.
Right. So somehow psi hat you're expressing as a sum of vectors in the kernel of A transpose and y transpose log x, which is
the image of y transpose, because log x was some, okay. Yeah, because log x or whatever x, it doesn't matter. It's y transpose acting on something. And what it spits out is something that lives in the image of y transpose.
In the image of?
By definition, right? When I have a matrix acts on a column vector. If it spits out a non-zero, after the operation, if I get a non-zero column vector, that column vector lies in the image of that matrix. That's the definition of the image.
Okay.
Yeah, so it takes some, yeah. One has to get one's mind, one has to get one's mind around this, even if it's only linear algebra, but yeah. So, okay. Yes.
So the goal is to find x, right? Finally.
Yeah, or psi actually, right? I mean, if
right,
I find the correct,
right, yeah.
Okay. Yeah, if I find the right psi, then somehow
right combination, right? Yeah.
Yeah.
Okay.
So that's basically it. So now I found it. So in the sense that I'm guaranteed that if I find, this sort of combination of zero eigenvectors of all the blocks, and then I use this little bit of play that I have in multiplying, one set of components with some constant and another set of components by another constant, I'm guaranteed that I get this psi, which is this x to the y. And why am I guaranteed? Just because of this thing. So that's really a very little bit mind-blowing aspect of this thing, I think. Let's take an example, and then at least in our example, everything will be very nicely clear. And then the good thing is that it's more generally true than our example, of course. Okay, so maybe I get rid of all this stuff. And then when you get used to this, you can see that you can cut a lot of corners. We never have to write rate equations. Or I mean, if the only thing we're interested in is the fixed points, if the deficiency is 0, we never have to write rate equations. We just cut corners and find write an A and find the zero eigenvector. And that's basically it. Okay. Okay, so now let's do this example nicely. So here is our psi sitting nicely there. A bit dim, I think, for you on the screen, but I hope you can see it. We've written it several times before. That's what we want to find, right? If you actually solve those rate equations, like I asked you all to do yesterday in the tutorial, so I hope some of you did that. The rate equations actually in this particular case are not hard to, I mean, that's why I took that example. You can just solve them by hand, by brute force, okay? Then what you get is a psi like this. No, sorry. Yeah, sorry, 1 K3 bar by K3. So please check this. K4 bar by K4. And K3 bar by K3. K4 bar by K4. So you see, we got an XC, we got an XS, we got an XC times XS, which of course should just be the product of these two. But that just now it's not surprising. We solved the rate equation and we got this. And I just want to show you that we'll get the same thing if we just consider the kernel of A. Okay, you should all check that I'm not making all kinds of awful mistakes here, but I hope not. Okay, so we got something just by solving the rate equations. It's not hard. Yes, there it is. I shouldn't block your view. Fine. So now let's look at E. Let's just look at this E and let's try to just solve. So this is what we got solving rate equation. Okay, so this is from rate equation. Now let's look at the other case. A psi hat is equal to 0. That's in fact a very easy thing to solve, even a bit easier than solving the rate equations, because I just solve it like one block at a time. Okay, I solve that block and I solve that block and I put the two vectors together and I get something like this with some constants hanging around. I get psi hat is equal to A K3 bar by K3 A K4 bar by K4 B K1 by K1 bar and B K1 bar K2 bar K2. Okay. Remember that example we took of the deficiency, which was non-zero, and then we got a bit stuck. We couldn't actually fully write it in the form with the correct concentrations. Remember, these things are not just anything; they have a meaning. The first one is just 1, okay, corresponding to our phi. But the second one should be the concentration of E. The third one should be a concentration of S. The fourth one should be a product of these two. The fifth one, the concentration of ES. The sixth one, the product of the concentrations of E and P. So how are we able to do that? This deficiency zero theorem and all this juggling around with all these images and kernels and stuff like that is guaranteeing that I have just enough play to be able to set this correctly. So how would I set it here? Okay, I set A equal to 1. I mean, so two constants or one constant doesn't matter. I can take one constant out and then I'll have one, set of constants multiplying this. So I can set A equal to 1. So far, so good. So far, so good. So far, so good. And then if B should be XE times XS, I have some play here. So I set B equal to this. And then you can convince yourself that with B equal to K3 bar by K3 and K4 bar by K4, I'm able to get exactly this. Okay, hopefully I haven't made any mistake, but I don't think so. No. So I had that little bit of play with B and I was able to do this. So the image of Y doesn't, of course, lie directly in the kernel of A, but the image of Y massaged a bit in the way that I'm allowed to do lies in the kernel of A. Is that making sense? Let's take one other little example. We just do some shortcuts, and I think maybe then we will stop for today because what we want to do now after today is that we want to sort of go a bit beyond deterministic modeling, and we want to go to stochastic modeling, and the very same network, let's say, or a simpler one, maybe this example that I'll take, a simpler one, and then we will write the master equation down, okay, in all its gory detail. And then we'll see, however, that the steady state, there is a very simple solution for the steady state exactly related to deficiency 0, okay? Okay, so let's take another example just so that you get a little bit more familiarity with this, and that same example we'll continue with tomorrow. Okay, I actually erased that without meaning to, or rather, yeah, I did mean to, but I forgot to say something. And that is that in this particular case, you go back and check the solution is actually, well, there is this thing called complex balance. Complex balance just means that if something that is lying in the kernel of A is balancing complexes, right? It's not balancing species, it's balancing complexes. It's saying, so much of this complex got decreased. Okay, that means the corresponding increase at these rates in these other complexes. So that's why this term complex balance comes in. So complex balance is a sort of a wider class than detailed balance. But in this particular example that we took, actually, you can check that the solution actually is detailed balance. So we didn't have to go through this whole procedure. We could have done a very fast shortcut and taken just reactions, pairs of reactions, pairs at a time, and still got the solution, okay? But in general, that doesn't have to be the case. When something is detailed balance, of course, its stochastic version is also sort of time reversible. So that's where that's where this terminology of reversibility comes in. But here, when we say reversible, it doesn't actually, the stochastic version doesn't have to be time reversible, okay? But in this particular case, check that in fact, it is indeed detailed balance as well. But in general, there is this condition called complex balance. And when we look at master equations, we'll see that it provides a condition for reaching steady states. In fact, not just any steady state, it provides a condition for reaching factorized steady states. And that's again connected to this deficiency 0 condition. Okay, so that will be our main focus tomorrow. But let's just introduce this example that we are going to use tomorrow. So it's a bit smaller than that, so I thought I'd take that instead, just because once you start writing a master equation down, it's pretty long, even for this one. So let's take another example that's like this. A goes to 2A, goes to B, goes to C. Sorry, back A. I have my usual rate constants, K1, K1 bar, K2, K3. So if I wanted to find if I wanted to solve this deterministic set of rate equations for the fixed point means that I need a concentration for XA and XB. Basically, the rate equation is a equation for the evolution of the species, right? So the fixed point will give me a concentration of A, and it will give me a concentration of B. Now I can cut through the chase, go right to the end, just write the A matrix down. Remember our A matrix, the rows and the columns are labeled by my complexes. My complexes here are A, which is both a species and complex, 2A, which is a complex, and B, which is both a species and complex. And here I took this example where one way goes both and then the other is just single arrows. Okay, this is our weakly reversible. It's not reversible, it's a weakly reversible network. However, because it's weakly reversible, the deficiency zero theorem still applies for us. So if I write this A, it's minus K1 bar. Let me just do this fast. Okay. Oh, sorry, it's a K3. Yeah, sorry. This is a K3. And there wasn't any K2 bars. Okay, and we are guaranteed that the zero eigenvector of this is going to be actually exactly in the form XA, XA square, and XB. Okay, so whatever zero eigenvector I find, I'm guaranteed that it's going to be in this form. And you can check that, and those are easy to solve. Let me see. Yes. So the idea of the complex balance, I just wanted to, because it's going to be a bit important for us tomorrow, I just wanted to emphasize it a bit more. So complex balance, I think you can see this part of the board. Complex balance just means, in this context, in the determinative context, that I just, it's just telling me that I just look at the null space. If I want the fixed point, I look at the null space of this matrix A. So I just equate all the reactions. So I take all the reactions where a certain complex is the product, and I take all the reactions where that complex is sort of a reactant in some way, like a source, and then I equate those two. So that just corresponds to the null space of this, right? So K1 XA is equal to K1 bar XA square plus K3 XB. So this is K1 XA is all the reactions where this was the source, okay? K1 times XA going into something else. And K1 bar XA square is what's coming into A from this side, and then this one is what is coming into A from that side. So basically, I'm doing a kind of, you see, it's more general than detail balance, right? Detail balance, if indeed that was holding, like that it was holding in that reaction network, would mean, so this is complex balance. Detail balance, just to remind you, I'm taking an example, for example, in that network, example, one reaction would be K1 times XEXS is equal to, okay, maybe that's not such a good example. Let's take this other. So K1 bar plus K2 bar, no, so K1 bar XES is equal to K1 XEXS. Okay, what is, so you see, if you look up there, ES, the complex ES is changing because there are lots of things happening to it. Yeah, the E plus S could combine to form this enzyme substrate complex, or E plus P also could come back. You know, this P that dissociated, the products that dissociated for some reason could actually come back and join and form the enzyme substrate complex again, let's say. Okay, so normally I would think that a solution would imply that I take all the gain terms and all the loss terms and I equate it, right? So that's how I do it in the rate equation. But detailed balance tells you that no, there's even more. I just equate this reaction by reaction. It's enough. And if you check that solution, you'll see that in that particular case, that's actually enough. In this case, you see that I have to actually equate all reactions where something is the sort of source, and all the reactions where something is the sort of where it's being sort of provided. So and that gives me the solution, and then you can check that. Of course, I have two more equations corresponding to these. This one multiplied by that one is 0, and this one multiplied by that one is 0, and you can check. Okay, might as well just write it down. K1 XA K1 bar K2 XA square. So that gives me an XA direct. And then the last, which is not an independent condition, K2 XA square is equal to K3 XB. I hope you could see that. Okay, I think the last one was a bit cut, but anyway, it's just the last row. And so then you can see that XA from this equation is just K1 upon K1 bar by K2. K1 bar plus K2, sorry, and XB is K2 by K3 times XA square. Did that get cut off? No. That's K2, sorry, that looks like U here. K. Okay, so we sort of just raced ahead. We didn't need to write anything. We didn't even need to write Y or anything actually now. Now that we know the structure, we just race ahead and find a solution, okay? So the point is, and this we could do only if it's deficiency 0 for this sort of quite amazing reason that that's the only time where the space is spanned by the kernel of A transpose and the image of Y transpose.
Sorry, Supriya,
yes.
So why did you write this zero eigenvector in the form XA square and XB?
I just cutting to the chase. I don't have to do that. Yeah,
okay,
I mean,
so in
normally
general,
I should just write
X1, X2,
normally
X3,
I should write it as
okay.
exactly. I should write this actually. I just cut lots of steps, right? Because I know now that I will get that. I should actually write this as A, B, C, or X1, X2, X3, or whatever I call it.
Right,
right?
Yeah, okay.
And then solve it, and then ensure that I actually get that. This should be XA, and this should be XA square, and this should be XB. Right. So to be correct, I should have just just written something and then shown you that, of course, the conditions are satisfied by the deficiency 0. But I can just rush to the chase. I mean, I can just cut to the chase, as they say, when I know now the whole structure. Deficiency 0. It's weakly reversible. Fine. Then I know unique fixed point lying in the kernel, and I'm guaranteed that that's all. That's it. Okay.
Okay.
And
So basically,
that,
if I
yes,
find psi hat in this case, it's guaranteed to have this structure because of whatever
yeah.
there. Okay.
Yeah. And you see that it's so much easier to just find the 0 eigenvector of the A matrix.
Right, okay.
Or some linear combination of the 0 eigenvectors, which then I can fix the constants such that they are exactly the vector I want in terms of concentrations. Okay, and I think with that, I'll stop now. It's also time. Tomorrow, we'll start thinking about not deterministic modeling anymore, but stochastic modeling. So tomorrow we'll start with writing a master equation now. So this might be a good time to actually just think a little bit about, oh, if I had to write a master equation for this, how would I do it? Now, what do I have? I mean, remember the rate equation was just in terms of XA and XB. Now the master equation will be a probability evolution equation for this quantity P of N A N A N B. Okay. So we'll write the probability evolution equation for that, and then we will see that it's going to, how we can solve it, actually using this condition, this sort of equivalent of this condition called complex balance. And that is the work done by Anderson, Krasien, and Kurtz in 2010. Okay, thank you.
Okay.
So for the tutorial, I thought that we will, sorry, Abhishek, I just wanted to say that tutorial, I thought that we will keep it free. I mean, I'm sure you'll have plenty of questions, right? So
Yeah, people can ask like if there are any questions, I guess. Yeah.
Yeah, yeah. I mean, you can ask now too, and also in the tutorial.
Okay, I don't see any questions, so maybe we stop now.
Hmm?
Okay.
So I will join in
6:45.
6:45 your time.
Yeah,
Yeah.
around then.
Yeah, I'll do that.
Okay, thanks. Nice.
Yeah,
Yeah, see you tomorrow. Bye.
Bye.